Given that f of x is bounded by 3 and 5, including the endpoints, and x is bounded by negative 3 and 5, including the endpoints, estimate the given integral from minus 3 to 5 f of x dx. Now we're going to use one of the comparison properties of definite integrals. There are actually several of them. We're going to use the first one. If f and g are continuous functions, then the first property says if f of x is bounded by some constants like small m and capital M, in our cases it's 3 and 5, so let's write this down. Small m is 3, capital M is 5. For x being between a and b, and let's write down in our case, a is minus 3 and b is 5, then, and here is the most important table, we can, instead of finding the exact value of the integral, which sometimes is impossible, we can at least know some approximation of it. So estimation of the integral. Is it between 100 and a billion, 0.5 and 0.10? Well, it actually gives us some nice approximation over here. The answer will be, so then, we also need to figure out that the function f is continuous, but I think they mentioned that. Hope they mentioned that because that's kind of important. Then we can say that integral from minus 3 to 5, as you can see, a and b they both go to the limits of integration. F of x dx will be bounded by, and that's the official terminology, bounded by small m. Look at the left-hand side of the inequality. Kind of made it too messy. Let me do it like this. Here you go. Small m, which is 3, multiplied by b minus a, which is 5 minus 3. So it's going to be 5 plus 3. And it also will be bounded by, this is the upper bound, capital M, which is 5, multiplied by the same number, b minus a. And now, because I have more space, I'll write down 5 minus negative 3. So you knew where 5 plus 3 came from. So that's what we used. We used the numbers they gave us. The final answer will be, thus, the integral from minus 3 to 5 f of x dx is bounded by 3 multiplied by 8 is 24. And then 5 multiplied by 8 is 40. So now we know this integral is not from a billion to 2 billions or negative 100 to negative 1. It's from 24 to 40. And sometimes this approximation is good enough for further work with the integrals. There are more properties of comparison of definite integrals, which if one function is always smaller than another one, then the integral will be always smaller than another one. That makes sense if you see integrals as area below the graphs. That's why I decided to show you the idea. The function we were given here is not known. We don't know in the graph of it. We don't know the expression of it. But we do know, as you remember from the very beginning, that this f of x is from 3 to 5. F of x means the height is bounded from level 3 to level 5, right? So I will put here y equals a. In our case, it was small m, which was 3, and capital M, which was 5. So the function is kind of in this tunnel, right? So we know at least that, the function is not jumping higher than 5 or lower than level 3. Then they told us that the input is also fixed. The input is not like infinitely going everywhere. The input x was given between negative 3 and 5. So a was minus 3 and b was 5, which is not correct in this graph, but it's fine. I could just put like 0 over here and then it will be correct. So now a and b are also in the tunnel, right? Here is my restriction. Thus, this rectangle gives me the idea of where the function is located. But the integral of this function from a to b also can be represented as the area below the graph. Thus, this integral, which is all this area I just highlighted, this integral from -3 to 5 f of x dx will be between, and that is the area, right, in this case, will be also bounded by this rectangle. And rectangle has width and height. The width is, guess what? b minus a, right, which is 5 minus -3, which is 8. And height, guess what's happening with the height? Well, the lowest height will be 3 multiplied by b minus a. So, well, the lowest height will be 3. I'm already talking about the area, as you can see, because it's bounded by 3, y equals 3. And the highest height will be 5. Thus, we have two rectangles to mention. This function will be between the smaller rectangle, the function, I mean the integral, between the smaller rectangle and the larger rectangle. So those two rectangles gives me the upper and lower bound for the area. Area will be lower than the bigger rectangle, which was 5 times 8, but higher than this smaller rectangle, if you can understand my mess. The smaller rectangle is this one, which was 3 by 8. So that's how this theorem can be used to approximate integrals. And hopefully I did not confuse you with the idea behind the graph in front of you and how we use rectangles to put the function and the area below the function into some kind of box. And then this box gives us upper and lower bounds of the value we cannot find.